right, to draw resonance structure, you really need to keep in mind of these couple of rules. First of all, only lone pairs or pi electrons can be moved around. In other words, your sigma framework, your single bonds should never be moved around. Okay, remember sigma bonds are formed by head-on overlap, and those bonds are really stable. All right, so next, when you are drawing a number of resonance structures, make sure your electrons only move from electron-rich areas to the electron pair areas. Okay, understand that when there's any atoms that being electron rich, and those electrons are more possible to be relocated. Okay, and the other general criteria is when you are move lone pairs around, okay, those non-bonding electrons, you can only move it from an atom, right? A lone pair belongs to an atom, either to the atom's adjacent bond to form a pi bond. Well, more accurately, only from that atom to the atom's adjacent bond to form a pi bond. When you move number 4, when you move the pi bond electrons, and those electrons could either be moved to the adjacent atoms, okay, where the atom is forming a pi bond with its adjacent atom, you could move that pi bond electron to that atom or to the adjacent bonds. Okay? And very importantly, try to only move one pair of electrons at a time so you can write out all the possible resonance structures. Okay? And lastly, even when you have a neutral compounds, okay, you have a neutral compound, and you may still write resonance structure as long as you have multiple bonds, okay, not only double bond, triple bond works too, that connecting atoms of different electronegativities. Under that circumstances, your pi electron could be moved to the atoms with greater electronegativities. Okay, let's look at the following examples. As I mentioned, when we are drawing the Lewis structure and resonance forms, and you only can move the pi electrons or lone pairs, okay? And keep in mind that you want to try to move electrons from electron-rich area to electron pair area. And that being said, and when you see there is a positive charge on the carbon, by the way, this formula is like a combination of bond line formula and the Lewis structure. So where you don't see when any two bonds meet, those are carbon. So these are carbon backbones that carbon atoms is not reaching out. Okay, so when this carbon is having 3 sigma bonds, it has a formal charge. Under that circumstances, this carbon is electron deficient. Therefore, to move electrons around, and you found this pi electron right on the adjacent bond, so you can move the pi electron over. Okay. Also, I want to point out that, and these arrows are not really the kind of arrows when we do arrow pushing, when we write reaction mechanism. This is more like helping us to bookkeeping to make sure we have all the electrons that's needed. Okay, with that, you can draw a resonance structure here, and you have this new pi bond that's generated, okay, with the hydrogen written down for the terminal carbon. I'll just simplify it, writing CH3 there. And then for this carbon that loses the double bond, this carbon has a positive formal charge now, okay? And let's fill up the rest of the atoms for the adjacent carbons, okay? Now you have a resonance structure written. And for this particular resonance structure, this electron deficient carbon is adjacent to another double bond. Therefore, that pi electron could be moved around again. Okay, I'm going to use the same notation. And so the pi electron could be moved over here. Okay. And under that circumstances, and you are going to draw the other resonance structure here. A backbone, right? CH3 there. Double bond here. And now our new double bond is formed over here. And with that, the carbon that is now losing that pi electron becomes positively charged. Okay, formal charged. These are the three resonance structure you could write out. When you do it step by step, moving one pair of electrons at a time, you're able to write out all the resonance structures for this cation. Okay, moving on, the next molecule, the next cation having a positive charge on the carbon over here, on the terminal carbon here. If you look at this Lewis structure, and if I ask you to draw a Lewis structure for this guy, and if you draw it like this, you're not going to get full points because you are missing something on the nitrogen. Notice that nitrogen is trivalent. The reason it's trivalent is because it has 5 valence electrons. For neutral nitrogen, there should also be a lone pair here. Okay, this is a correct and complete Lewis structure for this molecule. This lone pair is important, so you need to have that included. Okay, again, we're going to move electrons from electron rich to electron poor. Okay, so let me use my green, okay, to bookkeeping the electrons. So I'm able to write a resonance structure. This is a new pi bond that's generated on that carbon. There are 2 hydrogens bonded to it. Now the hydrogen is no longer positively charged. And what's become positively charged is this carbon. Okay, it loses its pi electron, so it becomes electron deficient. We've seen enough of the pi electron movement, and in this case, there is a carbon that's positively charged, electron deficient. There is a nitrogen that has a lone pair there. Okay, and this nitrogen with this lone pair could actually be moved around by moving to the lone pair to the adjacent bond. Okay, remember lone pair can be moved from an atom to the atom's adjacent bond, and therefore you can form a pi bond here. This is the new pi bond that's generated. Okay, under that circumstances, nitrogen now carries positive formal charge. Okay, so that way you're able to again systematically writing all the resonance structures for this cation. And if I ask you among the 3 resonance structures, which one is the major contributor or more important? Which one? If I number them as A, B, and C will be the major contributor or the most important resonance structure because all the carbons and nitrogens have octet. Okay, makes this resonance form particularly more stable. Okay, now let's look at a couple of anions. Okay, again, when you have anion that tells us that this carbon is electron rich. So to bookkeeping and how you are going to stabilize or delocalize the negative charge, you're going to move the lone pair to the adjacent bond. Notice that lone pair can only move from an atom to the atom's adjacent bond to form a pi bond. Okay? Under that circumstances, if I stop here, I would have this carbon forming 5 bonds, which is impossible, right? The carbon could only have octet. Under that circumstances, I could also move the pair of pi electron to the adjacent carbon. Okay, the reason I move it to the adjacent carbon is because by doing that, I'm able to eventually write out all the possible Lewis structure for this molecule. Okay, so this is our new pi bond. And this pi bond and this carbon, the pi bond is gone, and the carbon eventually carries the pair of lone pair. Okay, and this is another double bond for the terminal CH3, which is called a methyl group. I just went ahead to write CH3 there to save time. Okay, with that, I could move the lone pair one more time to form a pi bond here, and move this lone pair over here, and I'm able to draw the other resonance form. The new pi bond and the lone pair. Actually, let me draw out the hydrogen. We should have the hydrogen here too. Okay, and that CH3 negative charge. Very importantly, I'd like you to notice that for all the cases, all the 3 examples, and if your original structure have a net positive charge, each of the resonance forms should have a net positive charge. Okay, if your original structure has a negative charge, eventually each of your resonance forms should have a net negative charge. One more example, and this molecule structurally look very similar to the previous example, except there is a CO double bond here. Okay, that's the whole reason I am giving you this example. Similarly, the lone pair can be moved to the adjacent bond, and this pi electron can be moved to the carbon orbital. We are able to draw out the resonance structure here. Okay, so do I miss one more carbon? Let me start from the terminal over here, CH3, CO double bond, CC double bond. Now this double bond is gone. Hold on. With this hydrogen, this lone pair is here, and the new double bond is over here. Okay, so with that, if you ever wanted to feel a little confused, you wanted to number your elements on the backbone, you could always number that. Okay, for instance, you could number this as carbon number 1, 2, 3, 4, 5 over here, 6, and 7. So there are total 7 carbons in the main backbone here. Okay, so that way it's easier for you, if it's easier for you to bookkeeping everything, 3, 4, 5, and you write 6 and 7. Okay, and with this structure, similarly as what we see before, and this lone pair can be moved over to form a pi bond, and this lone pair can be moved over to form localize to this carbon. Again, I probably should have all the hydrogens related hydrogens written out here. Okay, so I can write the next resonance structure. And in this resonance structure, I have CH3, CO double bond, and on the adjacent carbon, there's a lone pair here, and there's a new double bond here, and a double bond here. Okay, I did not write out all the hydrogens, and when we talk about the bond line formula, I'll explain to you that's one of the easy way to draw the bond line formula. You could skip, you don't have to write out all the hydrogens, except when there's any atoms you are particularly interested at, you want to probably write out all the atoms bonded to it, makes it easier for you to bookkeeping the electrons. Okay, so next I'm gonna, let's see if I have any other color to use. Do I not have other colors to use? Oh, here we are. Maybe I'll use a brown. And in this resonance form, okay, and the lone pair is on this carbon, and there is a double bond here, even though it's not a carbon-carbon double bond, okay? And under that circumstances, you actually could move the lone pair to form a carbon-carbon pi bond here, and move the pi electron to the orbital of oxygen. Again, this is another structure that is really not correct if you are writing out. I asked you to write a Lewis structure of it because it doesn't have that lone pair on the oxygen. Okay, now I fill this up. And under that circumstances, I can draw out another resonance structure, which is CH3. Draw out all the backbones. Oh, I missed a double bond there, huh? And oxygen has that lone pair. And now oxygen having a negative formal charge. So for all the resonance forms here, right, and each of them have a net negative charge. And you can see that on these resonance forms, okay? So under that circumstances, for this anion, if I'm asking you to identify what is more important, and you may notice that for the anion, all the carbons and oxygens have octet, okay? And therefore, you have to move down when you try to identify which resonance form is more important and look for the following criteria, okay? And criteria B, if you have my handout of the resonance, rules of resonance, and criteria B calls for whichever structure has the most number of bonds. And for all the 4 resonance forms, they have identical number of bonds, okay? Criteria C, asking for whichever structure with the negative charge on the more electronegative atom and the positive charge on the less electronegative atom. Under that circumstances, this last structure is really the major or more important contributor to the resonance hybrid of this molecule. Hopefully I give you enough of the example of cations and anions. Very interestingly, even if you have a neutral molecule like this, okay, and like what I have in bullet number 6, and as long as you have a double bond that is between 2 atoms that are of different electronegativity, okay, here we have a 6-member ring, okay, these 6-member rings are all based on the carbon backbone, okay, and clearly with a carbon-oxygen double bond, and the electrons, the 4 electrons are not equally distributed between the 2 atoms, okay. under that circumstances, you could actually move the pi electron, again, just using the arrow to hypothetically helping us to bookkeeping the electrons. And again, there should be 2 lone pairs on the oxygen for the correct structure. Okay. Under that circumstances, you can draw out one of the resonance forms. And your formal charge is on the carbon, positive charge on carbon, negative charge is going to be on the oxygen. Okay, with this resonance form, notice that this positive charged carbon is right next to a carbon-carbon double bond. That being said, we could again move the pi electron over to write another resonance structure. Double bond here. And if you want to bookkeeping all the atoms, and on this carbon, okay, on this carbon, and this carbon forms 2 sigma bond with adjacent carbons and a pi bond. And so this carbon also bound to a hydrogen here. Okay, if you want to write it out, it's easier for you to bookkeeping everything and also realize that this carbon carries the positive formal charge. Okay, so the original molecule is neutral and the resonance forms have a neutral overall charge. Okay, so all 3 are good resonance structures for this neutral compound. Hopefully this gives you a good sense about how to draw the resonance forms. There are a few in-chapter problems that are very helpful as well. So make sure you practice as much as you could to really grasp this.